Thank you very much. So again, let me say спасибо and здравствуйте. I am Yutaka Kamada. It is my big honor and pleasure to talk about the status of ITER project and research plan update. And again, I deeply appreciate for allowing me to join remotely. Thank you very much. Okay, next page, please. Okay, so this is just the reminder of what is the ITER mission. So it's the demonstrate the scientific and technological feasibility of fusion power for peaceful purposes at the reactor scale. We have two representative targets. First one is controlled fusion plasma with DT fusion gain Q of 10. The other is to demonstrate the integrated fusion technology. So ITER is a place for the world to utilize for cultivating fusion science technology and also human resources. So we have 7 members, and I deeply appreciate the big effort of Russian colleagues, and not only Russian DA, but also the Russian Plasma Physics Society and colleagues have been sustaining the ITER project. I deeply appreciate. Okay, next page, please. So this is showing the key points of fusion plasma development by ITER. On the right-hand side, the high integrated plasma performance should be demonstrated by ITER. One representative thing is Q equal 10, the self-heating and burning plasma, where we need high density, high temperature, high energy confinement time, and high fuel purity. This kind of thing should be consistent with the heat and particle flux control right on the bottom. It's a diverter function. And in addition to that, ITER is aiming at Q equal 5 steady state operation, for which we need high power density and steady state sustainment of plasma current by full non-inductive current drive. And this Q equal 10, Q equal 5, and diverter function should be achieved with full disruption mitigation. So this is a very important point of the tokamak operation. On the left-hand side, you can see how big and heavy is the ITER tokamak. And the height is 30 meters, also diameter 30 meters. And the tokamak weight is 23,000 tons. And from the plasma operation point of view, allowable error field is the order of 10 to the minus force of the toroidal field. This means that for a device like ITER with 10-meter size, manufacture and assembly error should be within millimeter. This is very, very challenging thing for the ITER manufacture and assembly. So next page, please. So it is needless to say to you that ITER tokamak is constructed by the components derived from 7 members. So the integration of the assembly is this kind of big mixture and big team, but one team is needed. Okay, next page, please. So this is the top view of the ITER site now. The center, a little bit left-hand side, you can see the tokamak building and the assembly hall. And the right-hand side of that, you can see the cryogenic plant and also the electricity power plant. And very roughly speaking, for the construction of the building, more than 85% have been completed. Okay, next page, please. From here, I'm talking about some representative components. First one is the ITER magnetic system, which includes 18 toroidal field coils, 6 module central solenoid, and 6 colloidal field coils and field collection coils. Okay, today I'm very, very happy to tell you that almost manufacture is going very well. Next page, please. The first thing is on the toroidal field coils. It utilizes the niobium tin conductors. The conductors are coming from the 6 members, of course, including Russia, and went to Europe and Japan, and winding pack were fabricated, and then structure is attached to that, and in total 9 TF coils manufactured in Japan and 10 coils manufactured in Europe. The next page, please. Okay, then you can see this very large toroidal field coil. The height is 17 meters and the weight is 360 tons. The bottom area, you can see how small is human being there. And today I'm very, very happy to report to you that all 19 coils, including 18 coil plus 1 spare, manufacture have been completed. And we can say that the supply chain and mass production of this large superconducting coil have been already established under the ITER collaboration in the world. Next page, please. So this is showing the toroidal field coils. ITER has 6 toroidal field coils. Of course, PF1 was manufactured in Russia and delivered to the ITER site. Right-hand side, you can see the PF1 and the PF1 related to Russian and IO teams with big smiles. And now the only one remaining coil is the PF3. It will be completion of the manufacture will be in this year. So for the toroidal field coils, we can say that nearly completion of manufacture. Next, please. Okay, thank you. This is the central solenoid. And the central solenoid has 6 modules, and now manufacture is up to 4. And 2 central solenoid modules have been integrated, assembled in the ITER site like this. And its assembly and manufacture is also going well. Okay, next, please. So here, let me move on to the diverter. So as everybody here knows, that the diverter is the most challenging part of the tokamak. And how can we make a tokamak attractive or practical is up to the diverter function. So diverter dome is fabricated by Russia, and the 1-ton diverter dome full scale have been already the acceptance test has been already completed, and it showed a very good result. And in particular, the tungsten tiles, you can see so many tiles attached, and they are fabricated in Russia, have demonstrated thermal resistance under the heat cycle, up to 5 and 10 megawatt per square meters. It was a very good result. Next page, please. And as for the outer diverter target, that is fabricated by Japan, left-hand side is showing the outer vertical target OVT prototype. It was successfully assembled. And right-hand side figure is showing as a helium leak test of the prototype. Next page, please. In case of Europe is manufacturing left-hand side a cassette diverter cassette body. In total 54 cassette we are utilizing, and the right-hand side, the inner vertical target, similar to the outer vertical target in Japan. Next page, please. So these outer target and the inner target prototype have been high heat flux tested utilizing the Lemov Institute high heat flux test facility. The assembly, this kind of assembly prototype was successfully passed the 6,000 test cycle with the heat load up to 20 megawatt, both for Japanese and European targets. We deeply appreciate the big effort of the Lemov Institute for this kind of high heat flux test from Europe and from Japan. Thank you very much. Next page, please. The Russian manufacture is not only for diverter, of course. This is just one example. And the upper port manufacture is going very well and satisfying the accuracy. Okay, next page, please. Okay, from here, I'm introducing you briefly the assembly procedure. So this photograph is showing the installation of the cryostat base. It's very heavy, 1,350 tons. It was successfully settled in the tokamak pit in May 2020. Okay, next page, please. Above the cryostat base, we installed the cryostat lower cylinder parts like this, and it was August 2020. Next page, please. Then after that, we installed the lowest toroidal field coil number 6 from China, and also after that we installed number 5 PF. Also you can see is a gravity support of the toroidal field coils. This installation was completed in 2021. Next page, please. Then we installed the vacuum vessel sector module. So sector module is as a combination of the 40-degree vacuum vessel sector and 2 toroidal field coils. So we installed this first sector module into the tokamak pit in May 2022. Next page, please. After there was smooth, however. So frankly speaking, now the ITER is facing big challenges of the first of a kind component. This is the non-conformity of the manufacture of the vacuum vessel. So this photo is showing the side part of the vacuum vessel. And you can see the double wall structure and the inner wall and the outer wall. So this vacuum vessel sector is welded to the neighboring vacuum vessel by welding utilizing splice plate. For that manufacture and assembly, we need a very good accuracy of the welding bevels. However, we found that the rework of the bevels is needed through a combination of building up material and shaving excess material down through machining. So we decided to bring this vacuum vessel sector module out from the tokamak pit, and the outer area. Now we have started as a repair work. Please come to please next page. In addition to the vacuum vessel, we also found an issue that is as a thermal shield. We found the defect, which was identified due to the chlorine stress corrosion. So this photo is showing the thermal shield. You can see a very bright surface. It is silver coated. And however, for the silver coating, we utilized as a chloride, and the remaining chloride became as a reason of stress corrosion. And half, roughly speaking, half of the thermal shield we need to repair. The other half we need to remanufacture. So next page, please. So vacuum vessel and thermal shield need repair work. So we decided to do the repair work in the assembly hall. Like this, you can see the sector module 6 and the sector module 7. And we are now doing the repair work. But fortunately, building up and machining test R&D is showing very good result. And following that, we are now continuing as a repair work. And as a first repair work, sector module number 7, vacuum vessel sector 7, will be completed in this year, May or June. And we are reinstalling the sector module into the pit in next year. Okay, next page, please. So from here, I'm introducing you as a plant support system. This is showing the steady-state electric power supply system. It has been completed in 2019. And the remaining thing is reactive power supply area. And the manufacture and assembly will be soon completed, and we are starting the commissioning. Next page, please. Okay, so ITER has a huge heat rejection system, and it's a water cooling system of the site. And it needs 3 to 1.2 gigawatt of other heat. And as a manufacturer has been already, assembly has been already completed, and we have started the pre-commissioning. Next page, please. This is showing the cryo plant, cryogenic system producing and circulating the liquid helium for superconducting coils. And other installation assembly has been already completed, and we are now doing the commissioning. So next page, please. So now the cryo plant completed, and the power supply almost completed, and water cooling system okay. And 19 TF coil is on site, and Russian PF coil 1 on site. So we have decided for mitigation of the risk during the machine integration and commissioning, we are doing the toroidal field coil cold test at nominal current of 68 kiloamperes. And also we are testing Russian PF1 coil. Using this cryostat, now this cryostat, blue one, is under manufacture. And we are starting as a cold test from 2025. And we, of course, we are not testing all TF coils, but without affecting the overall construction schedule, we are trying to do a cold test as much as possible. Okay, next page, please. So up to here is the construction and assembly. From here, I'm talking about the latter half of my presentation. It is on the ITER new baseline, which will be proposed to the ITER Council in this year, June. So here, let me say 2 important things. First one is the staged safety demonstration. The other is for the minimizing technical risk, our new schedule is the technically feasible schedule. Okay, let me start from the upper one, staged safety demonstration. As written in the first bullet, so ITER is a facility that will explore new scientific territory. It is a very large step from present-day fusion devices, like JET or JET6 ASA, the very large gap, the very big step we have. So ITER will evolve to overcome many new findings and problems by itself. through its own operation. And the third bullet, given these kind of uncertainties, the safety demonstration of the ITER cannot be done, fulfilled at this stage in the full scope. But we can only be built along a planned roadmap based on the findings that ITER will attain its operation. So, for example, we cannot predict how much dust is produced by ITER operation and how much tritium are absorbed there. So, because of this kind of uncertainties, we cannot now make a clear prediction for the future operation. Therefore, we decided to take a staged safety demonstration. Later, I'm explaining more detail. And lower side, because of the needs of the repairment and also some delay of the manufacture of the major component, we decided to take the technically feasible schedule rather than best technically achievable schedule. So this is a new way of our schedule. Next page, please. So this is showing the reference scenario. But very roughly speaking, please at first watching the pink painted area, you can find AFP, and that is augmented first plasma phase, and it's an operation, first operation of ITER. And then we are moving to the DT1 phase. It consists of 5 campaigns, but the total amount of the neutron fluence up to the end of DT1 is about 1% of the full operation of ITER neutron fluence. Then we are moving to DT2 based upon the experience of DT1. So this is a basic strategy. And from the left-hand side, the pre-augmented first plasma assembly phase, now we are installing almost all invested components before AFP. This is the biggest difference from the previous ITER scenario. And we are installing, for example, a diverter before AFP, and we are also installing the ELM mitigation coil, for example. And after that, we are starting AFP after demonstration of the cryostat closure and full field operation. And we are soon producing the diverter plasma. And during this AFP, we are conducting the deuterium nuclear fusion operation. And plasma current will be increased up to 15 megampere by the end of AFP. So therefore, the AFP phase is as written in the middle of this slide. It demonstrates a basis of the industrial scale superconducting tokamak system and demonstrate the nuclear fusion operation with H mode and commission the plasma control and protection systems toward DT1. And during this AFP, we are installing 40 megawatt of ECH. Originally, it was 20, but we are increasing it additional 20 megawatt. We expect some contribution from Russia, but by utilizing 40 megawatt of ECH and 10 megawatt of ICRF, we are conducting AFP. Then after that, we are installing additional 27 megawatt of ECH and 33 megawatt of neutral beam and moving to the DT1 operation. And in the third campaign of DT1, we are aiming at the Q equal 10 short pulse. It means 50 seconds, for example. And then in the fourth campaign, we are demonstrating our mission goal of Q equal 10 long pulse 300 or 500 seconds with 500 megawatt of fusion power. Next page, please. Okay, now this is again listing up the key milestones of the ITER project. So left-hand side, red characters, our mission goal toward Q equal 10 and toward the demonstration of the integrated fusion engineer. The mission goal, superconducting coil manufacture completion, it is coming soon. And then tokamak assembly completion with high accuracy, 10 to the -4 accuracy, as I said, and full magnetic field achievement, and the diverter tokamak plasma equilibrium control, and nuclear operation with DT, and in DT, one phase with DT, and the tritium plant operation, and Q equal 10 short pulse, Q equal 10 long pulse, and Q equal 5 steady state. But in order to do that, we need very big development of plasma understanding and plasma control. Right-hand side, for the plasmas, we need high performance with tungsten first wall and diverter. Later, I'm coming back. And 100% of disruption mitigation by the SPI system, and error mitigation with RMP, and detached diverter at even at high Q operation, and burn control. And the lower area, integrated plasma modeling code should be prepared, and also plant simulator should be prepared and benchmarked. Okay, next page, please. So here, let me say that the ITER first wall armor material have been, the IO has decided to change from original beryllium to tungsten. I know very big effort has been done by Russian colleagues for the beryllium first wall, but here I'd like to say that, let me say that our IO's baseline is utilizing the tungsten first wall armor material. There are 4 important reasons. First one is we have concerns regarding the structural integrity after disruption damage. It is melting. If the beryllium first wall armor material is melted by the runaway electron, there's a large electric circuit is produced, and because of that, beryllium first wall cannot be kept safely kept even across other disruption. Therefore, IO decided to change the first wall armor material to tungsten with the higher melting temperature. And the second one is, of course, we need to achieve Q equal 10 with tungsten, and also the ITER needs to show the possibility of the tungsten wall to the demonstration reactor of fusion. The third one is saying that the erosion of beryllium is large, and this is a reason why the demo reactor cannot utilize the beryllium. The fourth one is the beryllium has some toxicity. So because of these reasons, but mainly the first one is the biggest newly appearing reasons. So this kind of decision make was done. So next page, please. But of course, we have concerns of the high Z material. This is tungsten, which enhances the radiation from the core plasma, and the risk to achieve Q equal 10 ITER target is increasing. And up to now, IO collaborating with the world modelers, we did the impact assessment. And the Q equal 10 can be sustained up to the highest tungsten wall source modeled. However, for the risk mitigation, we need to prepare the boronization system. And in particular, in addition to the usual boronization utilizing glow discharge cleaning, we are thinking about the installation of a boron dropper kind of things. And up to now, we have collaborating with the ITPA, International Tokamak Physics Activity, and we received, up to now, there's no showstoppers found But of course, we need to continue our R&D utilizing so many material tests, and also the test utilizing the existing world tokamaks. Next page, please. One of the important R&D is the characterization of alternative low-Z coating in the surface of the tungsten, first of all. So Russian Federation Domestic Agency, RFDA, and IO are now discussing R&D program as a ITER task on the use of B4C coating on the tungsten as an alternative risk mitigation to reduce tungsten influx into the ITER plasmas. These coatings have been already developed in Russia, very good, to a thickness up to 20 micrometers by a range of the techniques for which can be utilized in ITER. So today, because of short time, I cannot explain the detail, but this kind of material test collaboration is under way between RFDA and IO. So if you are interested in, please join. Next page, please. So from here, I am again informing the listing up the AFP objectives of each period, and also risk mitigation or risk retired. So blue one is a risk mitigation items, but that means we need this kind of R&D together with the Russian colleagues and of course international colleagues. Okay, in this AFP, we are doing commission as a control and protection system with plasma up to 15 megaampere and full field 5.3 Tesla, and demonstrate disruption mitigation up to 15 megaamperes, and develop plasma scenarios up to 15 megaamperes, develop plasma scenarios up to 5 megaampere in H mode with deuterium, and also up to 15 megaampere with L mode. And the green characters, main risks to be retired, are listed here. Commission the control of the protection system with plasma, and disruption mitigation and plasma operation with tungsten wall, and the fast assessment of fuel retention. Okay, next page, please. In DT1, with the full heating power, 67 megawatt, ECH 33 megawatt, neutral beam, and 10 megawatt, or possibly 20 megawatt of ICRF. So we are doing the commission control and protection system up to Q equal 10, and demonstrate disruption mitigation up to Q equal 10, develop plasma scenario in DT up to 15 megaampere in H mode, or lower plasma current around 12.5 megaampere if Q equal 10 can be demonstrated with the hybrid scenario operation. So there are two kinds of reliable operations, we think. And one is the standard H mode scenario with 15 megaampere at Q95 over 3. However, thinking about the disruptivity and the easiness of the disruption mitigation, if Q95 can be increased up to 4, it's much better. And hybrid operation, of course, we need a higher energy confinement time, but hybrid operation is one of the main operation scheme of ITER. And in this DT1, the total amount of neutron fluence is 3 times 10 to the 25th. And this is 1% of the full neutron. But it is equivalent to 550 pulses of Q equal 10, 300 second. This kind of thing is now implanted in DT1. And the green areas, main risks, and it's of course an important thing to commission and control with additional heating power of 120 megawatt and fusion power of 500 megawatt with plasma stored energy of 350 megajoule and plasma current 15 megaamperes. And based on the achievement of DT1, after gathering the data, we are moving to DT2. Next page, please. And here is showing the specific contributions we are expecting from the world, of course, from the Russian devices and modelers. So it is not changed from the 2016 baseline. Of course, first one is determination of the error field from assembly, and low one-time voltage plasma startup, EC wall conditioning, and disruption load and mitigation, and runaway electron behaviors, and test some specific systems such as ECRF straight radiation sensors or steady state magnetic sensors, and validation of the negative ion source neutral beam shine through, and also the IMAS system. Next page, please. And so this page is showing the higher priority issues for the new baseline, in other words, utilizing the tungsten first wall. So fuel retention and removal from other volcanized layers, and use of alternatives to grow discharge cleaning for volcanization, and the tungsten impact on the limiter phase. And the fourth one is the largest area, and the tungsten impact on Q equal 10. The tungsten is produced from the wall, therefore wall source evaluation, and also it's a source screening, and pedestal transport and pedestal screening, and the core plasma tungsten transport. These are the lifetime of the tungsten in the tokamak discharge. So we need to have good modeling, and also it should be demonstrated utilizing the world tokamaks. So next page, please. So this kind of thing is under discussion in the ITER research plan update team. And ITER research plan update team is led by Alberto Duarte and Mario Merora, and 5 experts, 7 members. Of course, we have 5 experts, Russian experts in this update team. And now, good conclusion after the first meeting is written by Red. This team supported as a level 1 research strategy and duration for each integrated commissioning 1, 2, AFP, and DT1 and DT2. And this new ITER research plan will be reviewed in the coming Science Technology Advisory Committee, STAC 30 in May. So next page, please. So here, let me emphasize one important role of ITER toward a demonstration reactor. So plasma controllability is, needless to say to you, so one of the most important points. And we need to make the controllability as simply as possible for demo. So now ITER, a steering wheel, this is like the Formula 1 steering wheel. We need to measure so many things. We need to do so many controls. But based upon the experience of ITER, our demonstration reactor controllability should be much simplified. So this is the target, and I deeply appreciate the big collaboration from Russian colleagues in these areas. Next page, please. And also, the integrated modeling is a very important thing. There are so many things to be integrated in the good modeling. And should be tested utilizing the world tokamaks. And today I enjoy the Globus recent result. It was very exciting. And utilizing Globus, and this kind of integrated modeling should be benchmarked. And also ITER should be utilized for this kind of benchmarking, and also for demonstration reactor prediction. Next page, please. So ITER is located at the 1 step to demo. So by utilizing ITER, we need to demonstrate these important things as listed in this table: the component manufacture, assembly, and system integration, commissioning operation experiment, and also fusion code and standard of fusion regulation. But here I'd like to emphasize that implementation of the manufacture or assembly is not completion. In order to complete, we need evaluation. For example, 10 to the minus fourth accuracy of assembly is needed. That is requested from the plasma physics, how to avoid locked mode. However, if we can soften or relax this kind of requirement, our construction for demo will be much easier and cost will be reduced. That kind of evaluation from a physics point of view is very important. I deeply hope the colleagues, physics colleagues here to collaborate with this kind of evaluation. Next page, please. Thank you. This is my final page and the final remark. Let's construct and operate ITER together. And let's achieve ITER's milestone together. And also, please utilize ITER for your own Russian fusion development, including fostering next generation, fostering fusion industries, fostering fusion academia, and also decide on fusion regulation and code and standard utilizing ITER. Thank you very much for your kind participation to this talk. Спасибо. Thank you.